Okay. Seems like people have stopped entering. So this is the Git Parable. This is a 90-minute talk. If you're expecting to go out and get some beer in 45 minutes, you will be sorely disappointed. I'm sorry. My name is Johan Herland. I'm a software developer at Cisco Systems since 2011. I'm working on collaboration products, more specifically video conferencing. Before I worked at Opera Software for 7 years, and I've also meddled with Git and distributed version control since 2006-ish. At Opera, I started the migration from CVS to Git, and at Cisco, I was also involved in the migration from Subversion to Git. And I've also occasionally contributed some code to Git itself. Can everybody hear me, or should I put on the extra mic for the speakers, or is... Okay, I'm going to assume everything is good. If I'm going too fast at any point, feel free to stop me, or if something doesn't make sense to you. This is a starting point. If we get questions and we end up somewhere else, that's fine too. Also, I've been told by the organizers to make a public announcement. Basically, if there's a fire here, git commit, git push, and git out. So, the following story that you're about to hear, it's shamelessly stolen from Tom Preston-Werner, who was one of the guys that started GitHub. He made a blog post in 2009, so this is a quite old story. And I'm stealing his story basically because I'm lazy, but also it's the best introduction that I found to Git so far. Also, a fair warning, I made these slides fairly late at night, and I found that Google Docs supports animated slide transitions. Yeah, you'll see those. So, Git is a simple and powerful system. And often people try to teach Git by showing all the different Git commands. And then once they're sort of satisfied that they've covered most use cases, they basically yell, "Ta-da! That's Git." I don't do jazz hands. I don't believe this is the best approach to teach Git. It lets you use Git to perform some simple tasks, but the Git commands still feel like sort of magic incantations. Doing anything out of your ordinary workflow will feel terrifying because you only know those commands. And until you understand some basic concepts about Git, you'll feel like a stranger in a foreign land. So, instead, I'll tell you a story. Actually, I'm going to tell you a parable. I will take you on a journey through the creation of a system that's very similar to Git, from the ground up. And the concepts are very simple behind the system, but I feel that understanding the concepts is the most valuable thing you can do to understand and fully appreciate Git and learn to use it well. As I said, the concepts are very simple, but they allow for an amazing functionality, like Lego blocks, when you can build whatever you want. And hopefully, after hearing this parable, you should have everything you need to know to easily master the various Git commands and to become a Git power user. So, imagine that you have a simple computer and there's nothing on that computer except for a text editor and a few file system commands. And you've decided to write a large software program on this system. But you're a responsible software developer. So you must keep track of the versions of your code so that you can retrieve code that you've previously changed or deleted. And what follows is a story on how you might design this version control system and the reasoning behind those design choices. But first, before we start the project, Alfred. Alfred is a friend of yours. He works as a photographer. And he takes awkward family photos for a living, basically. Alfred tells you a story about Hazel, and she brings her daughter in every year at the same time. And she likes to remember what her daughter was like at each different stage, and as if these snapshots let her move back and forth in time to those saved memories. You suddenly see the ideal solution to your version control dilemma. So what you actually want are snapshots. You want snapshots sort of like save points in a video game. And basically, what if you could take these snapshots of your code base at any time and then resurrect those snapshots later if you want to basically restart from somewhere else. So you go back to your computer and you start working. You basically start with a directory called working. That's where you basically keep your code base. And you try to write one feature at a time. And when you complete a self-contained portion of a feature, you basically copy your entire working directory so that you basically have that version of that code in a separate directory. But you're going to make a lot of these copies. So you're basically renaming it to snapshot.0. So that's your first snapshot. Now the key here is you will never again change anything inside snapshot.0. It's just a snapshot of what the code looked like at that point in time. So you do some more work and you create a new snapshot. And you keep going. Now, to remember what kind of changes happened in each snapshot, you basically add a special file called message, where you basically note down the date when you made that snapshot and some comment about what you did there. And you put that message file within the snapshot. And you do that for all the different snapshots. So now, if you want to find a specific change, you can search through these message files to basically find the note you made when you introduced that change and when you did it. So after some time, you basically get to something that you're ready to release. And you basically decide to release this snapshot 99 as your version 1.0. So you package it up and release it, and your users love it. And you push forward, determined to make the next version an even greater success. So you keep coding, keep adding more features. But then bug reports starts coming in. People are not so happy with your software after all. These bug reports are made against your version 1.0 or your snapshot 99. So what you do is, in order to fix those bugs, you copy the code inside snapshots 99 into your working directory. And now you can fix those bugs. But then a problem becomes apparent. So your version control system up till this point deals very well with linear development. But for the first time, you need to create a new snapshot that is not a direct descendant of the previous snapshot. So your snapshot 110 here, with the bug fixes for version 1.0, it doesn't directly descend from 109. It descends from 99. So how do you deal with that? You're sort of breaking the linear flow. Clearly, you need something more powerful than a linear system. But it's time to have a break, and you take a walk outside. Outside, you walk past an oak tree, and you look more closely at the oak tree and the structure of the tree and the branches, and you start looking at the branch tip and how you can follow it back to the branch root and to the root of the tree. So the tree is a very complex structure, but the rules for finding your way back to the root of the tree are so simple, and they're perfect for keeping track of multiple lines of development. So you have another epiphany. By looking at your code history as a tree, you can basically solve this problem of ancestry. Which snapshot did I come from? So you need each snapshot to point to the previous snapshot all the way back to the root. So the first snapshot you made don't have a parent, but all the other ones basically point back to the previous snapshot. So how do you store this pointer? So we need snapshot 1 to point back to snapshot 0. Well, you can add a note in this message file saying that, this snapshot, the parent of this snapshot is snapshot 0. So you just add that into the message file, and you've solved your problem. Now, this pointer enables you to accurately trace the history all the way back to the root. And now your code history has basically become a tree instead of just a line. So, at this point though, after doing this development and the bug fix on version 1.0, you don't really have one latest snapshot anymore. You have two latest snapshots. You have the one where you did your most recent development, but you also have this one where you made the bug fixes to version 1. This idea of organizing things as a tree might lead you to want to make more lines of development. You might want to say, make some bug fix based on some earlier version, or you might keep developing your mainline development, or you might find other bug fixes to make on your version 1. So you'll have to keep track of all these different branches. How do how do you not lose track of your branches? So when you create a branch like this, you typically associate some meaning to it. So in this case, when you sort of look at this latest snapshot, you sort of think of that, okay, this is my master branch. This is where my main development happens. This is where I add new features. And this is sort of your version 1 maintenance branch. So basically, you add another text file. This text file lives outside your working tree. You just call it branches. And here you basically make a point saying that, I have a master branch. Right now it's pointing to snapshot 109. So 109 is the latest snapshot on my master branch. And my 110 snapshot is my latest snapshot on what I would call the version 1.0 maintenance branch. And if you want to switch to a given branch, you basically look up this file, you figure out, which is the snapshot for this branch, and then you copy that directory into your working directory, and you can start working on it. So, because you're only storing the latest snapshot on each branch, when you create a new snapshot, you need to make another step. So, when the new snapshot is created as part of a branch, you need to update the branch pointer from this file. So here, after 110, if I make another change on that branch, 111, I create the 111 snapshot. Inside there is a message file pointing back to 110. That's this arrow. But also in my branches file, I need to update my 1.0 maint pointer, saying that, this is no longer 110, it's now 111. But that's a small price to pay for being able to keep track of everything. After using branches for a while, you notice that you want to make a different kind of reference to snapshots. So you want to keep track of some snapshots, but not with the aim of changing them later, but with the aim of just remembering that, this is one important snapshot. So say, let's see here. There's an error in the slides here. But basically, you want to remember snapshot 99. That was the version 1.0. So you want to call that 1.0. You want to put a name to it. And with the same thing, when you bug fixed version 1.0 and you probably released this as 101 or something like that, you want to remember that name as well. So you take these names and the snapshots they link to, and you store that in a separate file, and you call that file tags. That's basically just tags pointing to snapshots that you want to give a special name to. Now, working on your own gets pretty lonely. Wouldn't it be nice if you could invite a friend to work on your product with you? You're in luck. Your friend Zoe has a computer set up just like you, and she wants to help with the project. So you basically start by, you tell her all about your great version control system, and you basically send her a copy of all your snapshots and your branches and your tags, so she can enjoy the same benefits of the whole code history. And then obviously she has her own working directory where she does her work. It's great to have Zoe on the team, but she has a habit of taking long trips to faraway places without internet access. And as soon as she has the source code, she catches a flight to Patagonia, and you don't hear from her for a week. In the meantime, you both do a lot of coding. So when she finally gets back, you discover a critical flaw in your version control system. Because you've both been using the same numbering system, you each have directories named snapshot 114 and 115, but the code inside them is different. And to make matters worse, you don't even know who wrote the changes in each snapshot. Like, for now, you know that she wrote those changes, but if you try to combine them, you want to keep track of, who actually made these changes? So together, you devise a plan for dealing with these two problems. So now, in this message file where you're sort of storing metadata on your snapshots, you add some more information. First of all, you add a line noting who was the author. So here, I'm the author, and over here, Zoe is the author. And then you shouldn't, you basically discover that we shouldn't name our snapshots with simple numbers. We need something a bit more clever. So first of all, does everybody here know about SHA-1 or cryptographic hashes? Anybody feel like they need an introduction to that? OK, I'll assume SHA-1 is known. Good. So let's just take that message file and put it through SHA-1, and you will get a unique identifier for this metadata. And now let's just rename the snapshot folder with that ID instead. So now you won't have the problem that her changes are in a folder that has the same name as your changes. If these files are different, and they will be because at least the author is different and the date is probably different as well, then basically those two folders will also have different names. So they will never conflict. So you both update your code histories, renaming all your folders based on the SHA-1 of the message file. All down the code history. So now you have these folders, and now they have different names because the messages are different. With this updated naming scheme, you can now fetch all your snapshots from Zoe's computer and place them next to your existing snapshots. And for all the code history that's shared, those you already have those, so you only need to copy the stuff that Zoe has actually made on top. So you get those two folders, and they're basically sitting next to your snapshots as well. So now, suddenly, in your tree, you have code or snapshots that have been authored by you and also by Zoe. So this point is really important, so I'll repeat it. A snapshot is identified by the SHA-1 of the message file. And that uniquely identifies it and its parents. These snapshots can be created and moved around between computers without losing their identity or where they belong in the history of a project. The message file always says that, my parent snapshot is this one, and my parent snapshot is this one, and you can always trace the snapshots back down to the start of the history. Finally, you can share these snapshots as you see fit. If you have some experimental snapshots that you want to keep to yourself, you just don't make them available to Zoe. So you can have your own snapshots somewhere else if you're really secretive about something. Zoe's travel habits cause her to spend countless hours on airplanes and boats, and most of these places, the places that she visits, don't have readily available internet access. But at the end of the day, she spends more time offline than online. It's no surprise then that Zoe really raves about your version control system, because all of the day-to-day operations that she does, she can do those locally. She don't need internet access. Everything, the whole code history is available on her laptop. The only time she needs a network connection is basically when you share changes. So let's simplify our drawings a little. We don't need to draw this working directory. We can just assume it's always there. The branches and tags file, same thing. Instead, we'll add these labels that sort of point to where in the code history the branches and tags are currently at. The green ones are for branches. So we have this version 1.0 maintenance branch here. We have the master branch, and I added a branch called math for the new work that Zoe did. And here are the tags. So we have the version 1.0 tag that we released, and then we have the bug fixed 1.01 version. Finally, let's draw the snapshots as simple dots. These are like, we can still think of them as folders with parent pointers back, but let's just draw them as simple dots. The arrows in the previous diagram, they're always pointing down, so back into history. So we can just draw them as simple lines instead, and we have these simple graphs. So here's the root of the project, and basically time and development flows upwards. Now, before Zoe left on her trip, you asked her to do some, to start working off of the branch that we've called math, to implement a function that, say, generates prime numbers or something. And she's done so. She's made 3 new snapshots on that branch. But in the meantime, you were also developing on the math branch. So you were writing, say, a different function to generate magic numbers or something. So you made these 2 snapshots. Now that Zoe has returned, you're faced with the task of merging her work and your work. But how do you do that? So, in the working directory, you can copy the changes made on both branches and you can reconcile the differences. So she added a function, okay, you'll keep that function that she added. You added a function, make sure that that's still there. And you basically create a new snapshot in your working directory containing the merged result of those changes. But now, you need to create a snapshot from that working directory. There's something special about this snapshot because it derives not only from your previous state, but it also derives from her previous state. So the first parent of this new snapshot is your work, and you can add a second parent to the same snapshot, which is her work. This is our first snapshot that has more than one parent. Once you've completed the merge, Zoe can just fetch all the snapshots that she didn't already have, so basically your two blue ones and the merge, onto her computer. And your histories match exactly, and you can keep working. You basically synchronize your histories. Now, like many software developers, you have a compulsion to keep your code clean and very well organized. And you also have the desire to keep your code history well groomed. But last night you came home after having a few too many pints of Guinness. You started coding and you produced a handful of snapshots. This morning when you look at that code, yeah, it makes you cringe a little bit. Well, actually, the end result of the code is pretty good, but you made some mistakes on the way, and you'd like to sort of clean those up. You don't want that messy history to sort of stay around. So let's say the branch on which you did your drunken development is called drunk, and you made three snapshots after you got home from the bar. Now, as a small aside, let's invent some notation here to just talk about different snapshots. So if the name drunk points to this latest snapshot, let's invent this name, drunk carrot or hat, drunk hat, to point to the parent of that snapshot. And then we can keep going and basically say drunk hat is the grandparent. So that's basically just a way of naming commits that aren't directly at the tip of your history, but further back. Now, say that the end result of this drunk branch, basically what you did along this branch when you look at it now is, okay, you did two different things. You changed an existing function foo to do something else, and then you added a new file called bar. You'd really like these three lousy snapshots to be two cleaner snapshots. One that changes the existing function foo, and another snapshot that just adds the new file bar. So you basically take the end result here from the drunk development, you copy it into your working directory, and then you remove that bar file so that you're only left with the first change, the first change you want to record in a snapshot. And then you can create a new snapshot and use drunk hat, so basically the start of your drunk branch, as the parent for that snapshot. And this snapshot compared to this now simply changes that function foo and does the change you want to reflect in that snapshot. And then you can copy this drunk once again into the working and then just create a snapshot directly. Now the change from here to here will basically just be adding that second file bar. And you make a new snapshot based on that. So here's your sort of cleaned up history. Yeah, and the parent of that snapshot is obviously the previous snapshot you just made. And at this point, the only thing left to do is basically just move the drunk branch pointer over to point to this snapshot instead. These snapshots here, well, you don't care about them. Basically, you can delete them from the tree. They're not referenced by any branches, so if you go looking at your code history later, you probably won't find them at all because they're not referenced by any of these branches. You can delete them from the snapshots directory if you want to. Now, let's talk a bit about what we'll know as the staging area. Now, as much as you try to keep your new modifications related to a single feature or a single logical change, you sometimes get sidetracked and you start hacking on something completely different. And only halfway into that, you'd suddenly realize that, my working directory now sort of has a combination of two different things. I really should separate these two as two discrete snapshots. So to help you with this annoying situation, let's invent the concept of a staging directory. So next to your working directory, you create a staging, and this is sort of where you'll prepare the next snapshot. This is where you do all your development. It's where you do your builds. It's where you do your debugging, everything. But here, this is reserved for basically, this is the stuff that will go into the next snapshot. And each time you finish a snapshot, you first basically copy the code you want in that snapshot into the staging directory, and then you make this, and then you copy that into your snapshots folder and make it part of the history, and update the branch pointer and everything. So with these two different sets of changes, if you want to make a snapshot, or if these changes belong in that snapshot, you basically copy them over into staging. But if these other changes don't belong in the snapshot, you just leave them in working. You don't copy them into staging. And then when you make the snapshot, you'll get the you'll get them into the snapshot. These others are just left in working, not copied into staging. So separating this concept of where you're working and where you're creating a snapshot, it makes it much easier to specify what is included and what is not included into the next snapshot. You don't have to worry too much about making other accidental changes to your working directory, because it's what's in here in staging that actually becomes part of your snapshot. You have to be a bit careful though, because say you're changing a file called readme, and you first make one change, and okay, I want to make this part of the next snapshot, so I'll copy those changes into staging, and then you keep making some other changes into readme. Now you need to remember to copy those into staging as well if you want those changes to be part of the same snapshot. So the lesson is this basically: every new edit must be added to the staging area if it is to be part of the next snapshot. Now, with a working directory, a staging directory, and loads of snapshots lying around, it starts to get confusing as to where the specific code changes are and what are the differences from one directory to another. So you'll want to, like, the message file inside each snapshot, it only gives you a summary of what changed. It doesn't really tell you exactly what lines have changed. So you will want to look at, so what are the exact changes, for example, between working and staging? So basically, what is the work that I haven't staged for the next snapshot yet? Or what's the difference between what I'm working on right now and what's in one of these snapshots? What's the difference between what I've staged and the last snapshot? So basically, what will become the next snapshot if I make one right now? Or you'll want to see the difference between, say, what's the difference between my master branch or the latest snapshot here and the latest snapshot on the math branch. So let's introduce a diff algorithm. So a diff algorithm basically takes two folders. In this case, I'm taking staging and the working folder, and it spits out a result, which is basically a text listing the changes. So we're doing source code here, so it's all text-based. It's fairly nice and easy to look at changes. One thing you'll notice when you work with Git is that you'll sooner or later get used to reading diffs. It's a nice format for seeing what has changed, basically. So here we're basically saying that, okay, moving from staging into working, you'll have to remove this line and you'll have to add that line. So those are the changes between staging and working. And as you develop and you copy things from working into staging, you'll use this to see, okay, what's left to, what changes remain in working that are not in staging, and do I want to copy those as well into staging? It's also important to see how the staging area is different from the last snapshot. So you can use the same diff algorithm. You just select different directories to compare, and you get a different result, obviously. There are many other diffs you might want to see. You might want to see the changes introduced by specific snapshot, and they basically do that by diffing that snapshot against its immediate parent. Or you'll want to see the changes between branches. So basically, how far has the math branch diverged off of my master branch? Well, you can compare those two snapshots, and the diff output will tell you. Now, remember Zoe? After a few more trips around the world, she starts to complain that her hard drive is filling up with hundreds of nearly identical copies of the software. Remember that each of these snapshots is a full copy of your working directory at that point. So you have all these copies of your entire project from the entire history of everything. You two have been feeling that all this file duplication is wasteful, and after a bit of thinking, you come up with something very clever. You remember the SHA-1 algorithm? It produces a short string, well, relatively short string, that is unique for a given file contents. Now, starting with the very first snapshot in the project history, you start a big conversion process. First, you create a new directory called objects, where you're basically going to store all the stuff that you're now consolidating. And by the way, this is where the slide animation goes crazy. So you go into the first snapshots directory. You unpack that directory, or you basically just go into the directory structure, and you look at everything that's there. You create a temporary file somewhere, and for each file in the most deeply nested directory, so basically the sort of leaf nodes of your file structure, so in here, you perform the following 3 steps. Step 1. You take the file, you pull it through SHA-1, and you get this checksum. Step 2, you add an entry in the temporary file. The entry is so this is just a regular text file. There are 3 columns. We use the word blob. Some say it's an abbreviation for binary large object or something, but basically we'll just call it a blob. And we take the checksum that we just calculated, we put that in there, and we take the name of the file for which that checksum is the correct one, and we put that in the 3rd column. That's step 2. And the step 3 is basically, we take this file, we rename it using its checksum, and we put it into the objects directory. We repeat this process for the other 2 files. So we take file 2, we calculate the SHA-1, we take that SHA-1, we put it into the temporary file with the file name, and then we move the file into the objects directory, renaming it with its SHA-1 sum. Same thing for the last file here. Calculate the SHA-1, put it into the temporary file, move the file into the objects directory.
So does objects directory now contain 3 files?
Yeah, objects directory contains 3 files, file 1, 2, and 3, but renamed using the SHA sums. And then this temporary file. You take that temporary file, which has 3 lines, 1 for each file. You put it through the SHA-1, and you get the SHA-1 sum for the temporary file. And then you put the temporary file also into the objects directory, named by its SHA-1 sum. So note that the contents of this temporary file, it exactly mirrors the directory listing of this directory here. We'll use this fact in the next phase. So now we move up 1 directory and we start over. So for this directory here, sub-dir 1, we want to create an entry. It doesn't make sense to take the directory itself and pull through SHA-1, but we use this temporary file, the directory listing we made in the last step, and we use the SHA-1 sum of that to identify sub-dir 1. And this is a tree. We call that a tree instead of a blob because it represents a directory and not a regular file. At this level, there's also a regular file. We pull it through SHA-1, we get in SHA-sum, we record that in the temporary file with the file name, it's a blob, and then we move that file into the objects as well. And when we finish this directory, we do the same thing. We take the temporary file, pull it through SHA-1, we get the SHA-sum for the temporary file, and we put it into objects. And in this fashion, you can build a tree of directory object files that contain the SHA-1s and the names of the files and directories or directory objects that they contain. So you sort of recreate the whole directory structure, but with these temporary files and their SHA-1 sums, and it's all stored inside objects. Once this has been accomplished for all the directories and files in your snapshot, you're left with one SHA-sum, which is basically represents the contents of the top directory in your snapshot. Now, you need to record this SHA-1 somewhere, but where? Well, you have this message file within the snapshot. So you can pull up this message file and you can add a line saying that, the contents of this snapshot is identified by this SHA-sum that points to this tree, which is inside objects. And now, this changes the message file, so it also changes the name of the snapshot itself, because that's calculated from the SHA-1 sum of the message file. So the uniqueness of SHA-1 of the message now also depends on the entire contents of your snapshot. All the files and directories have gone into the calculation of that line, and that line goes into the calculation of the name of the snapshot. It's also convenient to create sort of an object in your objects directory from the message file itself, the same way you do for blobs and trees. So we take the contents here, we pull it through SHA-1. This is the name, the new name of the snapshot, and we store this message file inside objects under that name. And this is known, or we'll call this a commit object. So now we have three different kinds of objects inside our objects directory. We have commit objects, which are basically these text files. And then we have tree objects, which represent the directories of our directory structure. And we have blob objects, which represents files within those directories. And since you're maintaining this list of branches and tags, you can now use this SHA-1 sum to identify where a branch is pointing. So this is the identifier for a whole snapshot. And you can use that when you record it into the branches file or into the tags file. With all this information stored in the objects directory, you can now safely delete the snapshots directory itself, because everything is inside objects. If you want to reconstitute the snapshots at a later date, you basically just follow the SHA-1s into objects, and you basically sort of pull out the files that are referenced from the trees and blobs and recreate the whole directory structure. Now, for this single snapshot down here, this whole process doesn't really give you much at all. You're still using the same disk space. They're just now all different files inside objects, but they're still the same size. All the files are still there. You haven't saved anything. You basically just converted one type of file system into a different kind of file system. And you've done a lot of work in the process. But once you start transforming the second snapshot, you discover something. Many of the files and directories in the second snapshot haven't changed from the first snapshot. They're the same files. And when you pull them through the SHA-1 process, they'll get the same names. So you'll end up reusing a lot of the objects from your first snapshot in your second snapshot. The only new objects you need to add into objects are for the files and directories that were changed in the second snapshot. So imagine two sequential snapshots in which only a single file in the top directory changed. If the snapshot otherwise contains, like, say, 10 different directories and 100 files, your transformation process will create first you'll get 10 trees and 100 blobs from the first snapshot, but for the second snapshot you'll only get one additional tree and one additional blob. And the real benefit comes when you do this across the whole history, because basically what you get is the objects that corresponds to changes in your system and not full copies of every snapshot. By doing this, you drastically reduce the number of files that are stored on the disk. Instead of storing nearly 50 identical copies of a rarely changed file, you only need to keep one copy. Eliminating this duplication between snapshots reduces the total storage size, but you can go even further, because we're dealing with source code here. It's just text. It compresses really well. So each of those object files inside the objects directory, you can just pull them through setlib and save even more space. So now you get to the point where the objects directory actually takes a surprisingly small amount of space, but still contains your entire project history. ta-da! This is basically Git. This is the fundamental core concepts of Git. What you have created here, this version control system, is actually a reasonable approximation of what Git does. The main difference is that Git gives you command line tools to handle a lot of higher level operations. Git uses the term commit instead of snapshot. That should be obvious by now. Git gives you a lot of other tools for looking through the history, keeping your branch tips up to date, fetching changes from other people. The diff algorithm I talked about, it's all built into Git, and hundreds of other common and not so common tasks. And finally, to sort of get you started with Git, I assume most of you might have used Git already, but this is sort of this is the point where you start introducing Git commands. First, when you start using Git, you should tell Git who you are. Basically, configure your user.name and your user.email so that when you create these snapshots, the author line that identifies who made these commits, it actually makes sense. If you want help on a Git command, git command -h gives you a fairly short help on the command line. Git help with a command gives you a much larger manual page with all the options. It can be quite frightening at first to see the amount of options that some Git commands have. And the command line interface is not always as nice as we'd like it to be. But I found that the combination of looking at the manual page and searching through it for the words that you are looking for helps a lot. And to start a new Git repository, it's really simple. If you've come from like a centralized version control background, you're used to like, we need to set up a version control server somewhere and stuff like that. No, with Git you basically just do git init, and it starts. It creates a .git directory in your current directory, and in there is where it stores all your branches, your tags, the snapshots, everything I've shown you. So, to move changes from your working directory into the staging directory, that's what git add does. So add is basically about adding changes to be put into the next commit. And then to make a new snapshot from that staging directory, that's what git commit does. And if you basically have a simple change and you basically just want to put into staging, get a snapshot from it in one command, that's git commit -a. Takes all your changes in your working directory and just creates a snapshot directly, or a commit. Git log is what you use to look at the history of your project. So it basically starts listing your most recent snapshot at the top, and then the previous snapshot all the way back through history. And it has tons of options to limit what you're looking at, or limit it only to snapshots that change a certain part of the project or something like that. Git k is a nice GUI command that is pretty much git log but in a GUI. So it draws this nice graph that shows you the snapshots, just like the snapshots we've seen. And you can scroll up and down, you can search around, and you can look at the diffs and everything. And git status is really, really useful. It tells you it gives you a summary of the changes in your working directory, and also the changes in your staging directory. It'll list some changes are unstaged, basically meaning that these are changes in your working, but they haven't been replicated in the staging. They haven't been staged for commit yet, and all the changes have been staged. But it's a really, really nice command for just getting an overview of, okay, what's my current state? To see the differences between the working directory and the staging area, you can just use git diff without any arguments. So that defaults to basically, okay, what are the changes that I haven't yet staged for commit? And git diff -staged will then say, these are the changes that I have staged for commit. So basically the diff between what's in the staging directory and what's in the latest snapshot. If you want to see the diff from the latest snapshot across staging into working. So basically, what's the difference between my last commit and what's currently in my working directory? You basically git diff against head. So head is the magic name that Git uses for the last commit of the branch I'm currently on. And then you can use git diff from one snapshot to another snapshot. You just identify the two snapshots. Git branch shows you a list of your branches. You can also use git branch to create new branches, and then you use git checkout to change to that branch. And you can do both in one operation with the -b option to check out. Git tag -l lists your current tags, and to create a new tag, you basically do git tag and then the name of the tag, and that will create a tag pointing to your most recent commit, the commit you've sort of currently checked out. If you want to tag a different commit, you can just name that as a second parameter. To start talking to another Git repo, you use git remote add to tell Git about where to contact that repo, and then you give it a shorthand name. This name is called a remote. It's basically just a reference to some other Git repo. It might be on some other machine, it might be on the same machine, it might be over SSH, or it might be over HTTP. All that is sort of identified by the URL. And then you can use git fetch to just fetch changes from that remote. One important point that is worth noting is that when you run git fetch, it never changes anything in your working directory or your staging directory. It only fetches snapshots from that other remote, but it doesn't change anything you're working on right now. Basically, in order to actually integrate changes from someone else into your changes, you need to run a git merge. So that sets up the whole merge process where you get conflict markers if Git is not able to automatically resolve the differences. And you basically call it by saying, so if I have a remote called, in my case, or in the example here, I'd probably have a remote called Zoe, which is the URL to her machine. I would say git fetch Zoe to get her changes onto my machine, and then I'd call git merge Zoe /master if I'm merging her master branch to actually integrate those changes with combine those changes with my own so that I can get the conflicts and resolve them if I need to, and actually create that merge commit at top. And git pull is basically just this command followed by that command. It fetches the changes and does the merge. There is a rebase command there. I'm not covering rebase today. Rebase is a slightly more advanced topic, but basically git pull -- rebase is git fetch followed by git rebase instead of git merge. But it's important to note that git pull is not really a fundamental command in that it's a composite command. It does two things. And you can do the first half without worrying about changing what you're currently at. So you can see what someone else has done, look at their commits without having to start the whole merge. As you continue to learn Git, keep this parable in mind. Git is really very simple underneath. It doesn't look simple at all when you look at the manual pages and all the options and all the commands and what you can do and yeah. But this simple design at the core is basically what makes it so flexible and so powerful. One thing to keep in mind as well, one last thing is remember that it's almost impossible to lose work that has been committed. If you have committed, if there's a snapshot of it, if you've told Git about these changes, Git will work very hard to remember those changes. Even when you delete a branch, all that you really delete is this label. The commits, all the snapshots are still there. At some point, if you later do a garbage collect, Git might start removing snapshots that are not referenced by any branch. But really, just deleting a branch doesn't kill any all the snapshots will still be in the objects directory. You just need to find the SHA-1 if you're missing something. And in those cases, git reflog is really, really useful. Git reflog is basically just a text log that keeps track of where your branches have been pointing in time. So say you end up somehow losing your master branch, or I know that I had this code checked out yesterday, but I lost track of it somehow. You can look up git reflog and say the reflog for your head, which is basically where were you checked out at any point in time. You can just go down the log and look at the dates and figure out, on this date I was checked out there. That's the SHA-1 for the commit I was checked out on. And then you can maybe create a new branch that points to that commit and sort of restart from there. Reflog is really, really useful if you've messed up and lost track of your branches or something. Here are some more resources. Git homepage has a link to ProGit. ProGit is a pretty good introductory book on Git. It shows you most of the workflows and commands. GitHub is obviously the biggest company sort of making a business around Git. It's where a lot of code is shared these days. And it's certainly a whole ecosystem of its own. A lot of people confuse Git and GitHub. GitHub is really totally separate from Git. It's there are core developers in Git that work for GitHub, but that's as close as it gets. There is nothing in Git that depends on GitHub. It's not like if GitHub went bankrupt, then Git would stop existing or something. I added 2 websites down here because they make it easy to sort of start experimenting with Git. Learn Git branching is basically a JavaScript website that lets you do Git commands, and it'll draw the graph of that you're creating with those commands right next to it. So you can do a Git commit and you can see the snapshot pop up, and you can switch branches. You can see basically what happens with this graph that I showed you when you do different commands. Git Ready is a nice site. It has a lot of sort of, I want to do this, what's the right command? Yeah, it's a different way of sort of learning various Git commands. So yeah, now go and become a Git master. Yeah, thanks. And questions? Yes?
Yeah. What are the main differences between Git and Subversion?
That is impossible to answer very shortly. So Subversion is a centralized version control system. You have a server somewhere that sits on the code and its history. When you start working on a Subversion project, you check out some version of that code. What is now on your machine locally is that version of the code, and actually a copy of that version as well, so that you can, when you do a Subversion diff, that is a local operation. But if you want to look at the history of Subversion, you need to talk to the server. If you need to commit something, obviously, you need to talk to the server because all the commits live on the server. This is such a fundamental difference that when you have a Subversion mental model and try to retrofit it onto Git commands, things become really surprising and confusing really quickly. Because something that, like, for example, the whole concept of a staging area, there's something where you prepare your next commit. The Subversion and lots of other version control systems don't have that. The whole idea that yeah, like check out, switching branches, it all needs to talk to the server. That's very different. I think it's a long time since I looked at Subversion. I think, for example, in Subversion, so if we go back here a few steps, look at this graph here, for example. Inside our snapshots, there's nothing in the snapshot itself that says that this snapshot was part of the master branch. No. I can have my master branch pointing here, and then I can take my math branch and point that there as well. And there is nothing inside the snapshot that says that, I belong to master, not math. these snapshots are just as much part of the master branch as they are of the math branch if the branch pointers point to or include those commits. So I think there is one big difference between Git and many other version control systems, because the commit itself will have some concept of I belong to this branch. You don't have that in Git. The branches are just labels that point somewhere into the commit graph. So yeah, that sort of just scratches the surface. But these differences in concepts make for a lot of confusion if you run a Git command that sounds like a subversion command and you expect it to behave like a subversion command. Sometimes it'll work fine, but sometimes it won't.
Just to tag on to that, I think one of the other big differences is that because the whole model is so different, in subversion you can branch, but merging is hell.
Yeah.
With Git, merging is possible, which enables us to do all these Git flows and feature branches, and which technically you can do with subversion.
Yeah.
But in reality,
yeah, and also this concept of having the commit as a graph structure where you can actually do merges merges like this one that has two parents and point into both lines of development that led up to them. That comes back to the same point in that so at this point when we merged Zoe's math branch into my math branch, if these commits had some internal concept of which branch I belong to, then this merge commit would have sort of a schizophrenic idea of, okay, which branch do I really belong to, because there's Zoe's math branch and there's my math branch. So yeah, these conceptual differences make it really, really hard to become productive with Git if you hang on to a centralized mental model. And this is the whole point of why I start talking about the mental model before I start talking about any Git commands. Okay.
And one important thing I see also, you don't have the staging part in subversion.
No, yeah, the staging part, that's sort of a design choice that Linus Torvalds made when he created Git, that he wanted that. You could envision a Git without a staging area, but once it's there, some people find it hard to sort of wrap their head around or learn how to use it properly, but once you get used to it, it's a really powerful concept. I use it a lot for, say, I have I'm doing 5 different things in my working directory at the same time, but I only stage the few things that I want in this commit. And it's a huge help in making sure that my commits are single issue, have a narrow focus, and have, it makes me much easier to write good commit messages as well.
But when you say that in Git you would work, those staging work that would happen locally on your computer, and you would not commit that to the server, is that what you're saying? So I mean, if your computer, if you've been working several days in the staging area, and you wouldn't like to commit it because that would somehow make the trunk it wouldn't compile or something like that. You would sit and work locally, and what could happen if your hard disk crashed? You lose all the work. Okay. Yeah. So the question is basically a commit in Git is a local operation. A commit is not reflected on the server. What happens if your computer crashes and you lose your work or something? And yes, this is one of the fundamental differences between Git or really between distributed version control systems and centralized version control systems. A commit in Git is local to your machine. Nobody else, not Zoe, not the server, not anybody, knows about that commit until you either push it or they pull it from you. There's a question back there first.
I have a question about the objects directory.
Yeah.
So if you apply a commit and one file changes, then do you copy the whole file or only the diff? Because it will take even less space if you copy the diff.
Yes.
It might be too long operation or else.
Yeah, so the question is basically when you create a commit and you basically move these files into the objects directory, do you move the whole file or do you just move the changes in that file? You move the whole file because yes, you would believe that if you just move the diff, you could save even more space. But then you would need the diff and the previous version and all the previous versions of that file in order to reconstruct it when you want to check it out later. It's much faster to reconstruct the file when you have the whole file there as one object. Also, I've told you the first half of the story. The objects directory, it actually works like I told you here when you start a new Git repo. But at some point, Git figures out that having all these objects lying around in one directory It's not efficient file system usage. So it has a repack process where it starts taking a lot of objects and packing them into one pack file. It's still the same format in that it's still identified with the same SHA-1 sums, and you pull it out in the same way. You just have some tools to help you do it. But when Git does that repacking, it then starts doing things like delta compression across objects to save even more space. So yes, Git does what you want, but it doesn't do it at the top level of the objects directory. It happens as an implementation detail further down into the tools. Patricia had a question first.
I was as a response to him
Yeah.
that if you want to push to the server, you can have a remote branch or your own branch on the server, and so you can push your changes there. So even though they don't compile, it doesn't bother anyone because it's your own branch there. And so you don't have to save everything locally. And then when you're ready, then you can push it to the master branch or to something that somebody else is using.
Yeah, so Patricia makes the point that you don't have to push to the master branch on the server, you can push to your own branch. A bold or an add-on to that answer is basically, this is also part of what makes, or why having the right mental model is important, because the way in which Git functions so differently from, say, Subversion enables whole new workflows, in that in Subversion, and especially in CVS and other, to some extent in other centralized version control system, a branch is a fairly heavyweight thing. Creating a new branch in Subversion is not something you do lightly. In Git, as I told you here, this branch, in your .git directory, if you go in and look at it, it's one file that is 41 bytes in length. So the concept of this branch is basically you have a file with a name. The name is v1.0-maint, and the contents of the file is 40 characters for the SHA-1 sum and a line break. That's the file that identifies your branch. And when a branch is such a lightweight concept, it's much easier to create lots of them. You throw away those you don't want. Tags, same story. So creating branches all over the place, well, like, the version control system is no longer the limiting factor on how many branches you want. It's basically how many you can keep track of. So yeah, whenever I work with Git locally, I start, like, I have an idea, like, okay, maybe if I do this to this class, it'll look nicer in the end, but I'm not quite sure now. I'm going to do an experiment. I'll start a new branch locally, just do a few commits, see how that experiment works out. Maybe it's really, really good and I merge it into my main branch and push it onto the server, or maybe it doesn't work out at all and I just throw away that branch. But creating a branch and removing it is it's literally creating a 41 byte file and removing it, and the tools do it for you, and it happens in the blink of an eye.
And then you can push the branch to the server if you want to.
Yeah, you can push the branch to the server if you want to. So in your collaboration environment, ideally, I hope everyone that works with Git have a nice Git server where they're able to push their own personal branches so that you have somewhere to back up your work without having to integrate it with everyone else and release it, basically. Yes?
So you have your experimental branch, right? So you created a few commits and then you say, okay, I don't like it, and you delete the branch. As you mentioned, it didn't actually delete the commits, so the files are actually in the object directory.
Yeah.
I know that Git has some kind of cleanup, but
Yeah.
what triggers it? Is it like automatic or what's...
Yeah, so basically, once you delete a branch, the commits themselves don't actually go away. There is a cleanup later. Does that look like? When does it happen? Is it automatic? Yes, there is an automatic garbage collection that is triggered by some Git commands. So say if you fetch, if you come into work every morning and you pull from the main repository, at some point you will have pulled down all these objects and they're starting to sort of bloat the disk, and pull or fetch internally will trigger, an automatic garbage collection. And that garbage collection will basically go through a repository, make an optimized pack file that is basically this magic file with all the delta compression, and that pack file will not contain stuff that is unreferenced. So that will not contain those commits that are no longer referenced by any branch. And then it will delete all the other stuff because the pack file has all you need, and that's when you lose those commits. You can also trigger this garbage collection explicitly by just running git gc. But you don't need to. There is an automatic fallback. Yes?
How does it merge if two people have worked on the exact same things?
Yeah. How does Git merge when two people work on the same things? So first, to sort of get the other stuff out of the way, when you have two branches, you're merging them. None of the or the branches change. The changes are in different files. Those files, it'll just take the changes and sort of meld them together. There are no conflicts as long as there are different files. If there are changes to the same file and the file is a text file, and the changes are in different parts of the file, Git will be smart enough to figure out that I can take this part here because it doesn't really conflict with this part up here, so I can sort of combine everything together and it'll be fine. So only when you have changes to a text file touching the same lines of code does Git basically throw its hands up and say, I don't know how to deal with this. And at that point, it'll spit out a file with conflict markers in it. So you'll have this in your text file, you'll have one line of these chevrons, basically saying that followed by the lines from one of those branches, and then you'll have a line of equal signs, and then you'll have the change from the other branch, and then a line of chevrons going the other way. And Git will basically tell you, there are conflicts here, you need to look at this and resolve these conflicts, basically create a version of the file where you have manually combined the changes into a way that makes sense, remove the conflict markers, and then when you're satisfied with what you had and you can build and test that in your working directory, then you can git add that file to tell Git that I've resolved these conflicts now. And when you do the git commit, it'll make the merge commit with your changes in it. So that's for text files. If you're merging binary files, things get more complicated. This is why we like version controlling text files and having source in our version control systems and not binaries. There are solutions, but they're too advanced to get into now. There's a question there.
Is it possible to build and test only what you have in the staging directory if you don't want to?
Is it possible to build and test only what you have in the staging directory? The staging directory is not actually a real directory on your system, so it's not like you can just cd into that directory and build and test. What you can do is there's a command called git stash. Git stash will basically take all the changes between working and staging, and it'll stash them away somewhere. You don't really need to know about where it is, but know that, okay, I can stash this away and I can get it back at some point. And when you have stashed those changes, what you're left with in your working directory, wait a minute, I think it's git stash dash dash.
Okay, no, I mean, normally when you stash them, you still have them.
Yeah, it's like a secret commit you don't look at.
Yeah. So under the hood, what Git actually does when you do git stash is it sort of creates a commit with your changes. But it's not a commit on your branches. It doesn't change your history or anything like that. But basically what you're left with is the stuff in the staging directory is now in your working directory. So your stage changes are left in your working, and you can now build your working directory and test them. And that will be basically the same as building and testing your staging. So git stash is a nice tool for basically, I have some changes here, but right now I just want to test or look at what is ready for commit. So I'll just put those changes away for a little while. I'll do my other stuff. And once I'm ready, I'm going to do a git stash pop. We'll basically take the last stash I made and put that back into my working directory. And you can continue working. Okay. There was another hand somewhere.
What will happen if you pull in the meantime before applying the stash?
So the stash itself, if we go under the hood again, and so stash is basically this sort of magic commit. That magic commit will have as its parent where you started from when you made the stash. So the stash will know what was the base state from which the stash applied to. So if you check out somewhere else and then you try to git stash pop, Git will basically try to merge those changes into where you're currently standing. And you might get conflicts, and at this point, things yeah, you need to keep your head straight, because at this point the changes from your stash might create conflicts with where you're checked out, and the conflicts marker will show up and tell you that this branch has a change here, and there's this other branch that has a change there, and one of those will be identified as stash changes or something like that, and you now need to sort of manually resolve that. So when you
Would it be showing the git diff or something?
yeah, so basically git stash pop will basically become the same thing as if you had done a merge between your state changes and your current head. And the conflicts, yeah, they'll show up in git status. Git status will see, there's this merge going on, and both branches had modified this file, and there'll be conflict markers there. But if you're lucky and your stash changes don't conflict with wherever else you have checked out in the meantime, it'll just apply the new changes, and you'll have your changes, but now based on top of your current commit and not where you originally started from. Yes?
Can I say something about merging strategies? Isn't it like when you merge, you can choose different strategies, and what should you choose?
Yes. Stick with the defaults if you don't know what you're doing. And that's sort of a regular good advice, I think. So Git has concept of merge strategies, which is basically how to deal with conflicts when merging. Well, there are two levels of merge strategies. There's basically how to deal with the merge proper, and then how to deal with conflicting changes. So first you can, I think it's git merge -s for the overall strategy, and there you can do stuff like git merge -s hours, hours as in hour changes. That basically tells Git that I want to merge this other branch into my branch, but I want the result to be identical to what I'm currently at. So I want to create a merge, but I want to discard all the changes from the other branch. It's useful in some cases, but you don't often need to do it. But then you have, like, you can do the other thing as well. Say that I'm somewhere else, I'm at some commit, but I'm not too fond of what's happening here. I have this other branch that someone else made. I just want to take their changes no matter what, and basically do a merge, but the end result should be identical to what they had. So then you can do, I think there's a git merge -s theirs that basically does that. I'm not sure if there are any other merge strategies that you would actually use in real life. But that's the sort of top level. Okay, how do we approach the merge as a whole? I want all those changes or all these changes. And then you have something called git merge -x, and then some other strategy. And that's more like, how do Git actually deal with conflicts in the same files? And that's, I think you get into those when you start, say, merging binary files. So like if you have one image here and there is another image and there are differences, like maybe you have some external program that can handle merging differences between images. And I don't remember off the top of my head, but it might be the git merge -x option that you use to sort of invoke that magic. Or yeah, I think you can do a similar hours and theirs thing, saying that if you have conflicting changes in this file, then always take my end of those changes, because I don't trust whatever came from the other branch or something like that. But yeah, there are, as I said previously, there are tons of options, and yeah, Git will let you do pretty much anything, but the manual page suffers from it because there are so many options.
You can always try and then reset if it doesn't work.
Yeah. So as I said, yeah, you have the reset command for resetting when resetting your branches or resetting your state to something else. So you can just experiment and see what happens. And worst case, you have the ref log. So if like, this really didn't work out, just get me back to where I was 5 minutes ago, then look up the ref log and it'll tell you where you were 5 minutes ago. Yes?
How is Git working with really huge projects? Like, what's the reading and storing to the repository, timings and performance and stuff like that?
Yeah.
Do you need a really huge disk on your computer and stuff like that?
How is Git working with really big repositories? The natural consequence of what I've told you today, everything is stored locally. So you'll need space for the entire project. not once, but twice. Well, I'll get into that. First, since everything is available locally on your disk, and the binary files, first of all, they compress badly, and sort of related to that, when you make a change in a binary file, it often rewrites the entire binary file. So if you just looked at a bitwise diff between an image and the later version of that image, it will be completely different. There's not like just this portion of the file changed. Binary files compress badly, and Git suffers from that, which is why we really advise people not to check in binaries, at least not large binaries and not many binaries, in your Git repo. Git does really, really well at delta compression and compression in general, and especially on things that compress well. So, for example, if you look at the Git kernel history, or say the history at my day job at Cisco, or many other codes, you'll see that when I check out a kernel repo, for example, I have a working directory. It's this big, say a gigabyte or something of code. And then you'd think that, but the .git directory has the entire project history. That must be so many times bigger, because there's history all the way back to, I guess, 1991 in that .git directory. But Git actually compresses source code so well that for most pure source code projects, the size of the .git directory is pretty much on the same order of magnitude as the size of one single version checked out. So typically for a source code project, if it takes n megabytes, then you'll need 2n megabytes of disk space to actually be able to clone and work on that repo. This is pretty much the same you get with Subversion, because with Subversion, what happens if you check out one version from the server, and Subversion internally stores a copy of that version inside the .svn directory. So you end up needing 2n space, where n is the size of the current version. But yeah, for binaries, it's not doing well because of all these design choices that I talked about. But there are tools. There's something called Git LFS. I think LFS stands for Large File Support or something like that. What happens then is that if you check in a binary file with Git LFS enabled, the binary file itself won't actually be checked into Git. The binary file will be uploaded to some asset server somewhere that is good at handling binaries, and then what will be checked into Git is some unique identifier or that references that asset from the server. And if you check out some version and it finds these references, it'll then pull those assets from the server and put them into a working directory. So you'll have binaries in your checkouts. They will look like regular binaries. You don't have to do anything special except enable Git LFS in the first. But yeah, you're on your day-to-day work, the files will just be there and it'll work. But you'll need to set up this infrastructure with this asset server and handling binaries specially. So there are solutions, but out of the box, Git doesn't do very well with binary files. That's a design decision. Like we have decided this. Basically, when Linus first made Git, he wanted to make a version control system for source code. Yes.
Just a comment to this last question, because for instance, if you use a system like Perforce, or I think also SVM, you might have like a big tree with every software part of the tree in the folder, but in Git you probably split into separate Git repositories for each part. So you don't collect everything in one big Git. In general, I find Git is fast compared to other systems.
Yeah, so yeah, the comment is basically about when you have big project structures, lots of directories. In Subversion, Perforce, other centralized systems, they can handle fairly big structures fairly well, and it's easy to say check out just a sub portion of the product. In Git, it's much easier to create multiple Git repos for parts of your project, but there are some downsides there as well, because if checking out your project is basically checking out this big hierarchy of many different Git repos, then you need to set up some infrastructure to make sure that you get the right version of the right repos every time, and you get mechanisms like submodules, which are often confusing to work with because suddenly you're working in 12 different Git repos at the same time and not just one. And yeah, I've seen examples going both ways, both like companies that have split their structure into many Git repos, but also projects that basically have monster Git repos, and it still seems to work somehow. Like current workstations are plenty fast, and SSDs make up for a lot of. You can check out a lot of crap if you have a fast disk.
It's not so often you clone either.
No, that's a good idea or a good point. Yeah, cloning is pretty much the only really expensive operation in Git, because that's when you actually talk to the server and you pull down the whole project history. After that, the only communication that you have with other Git repos is just pulling and pushing changes, and the changes are just what has changed actually. So yeah, when you do a Git clone of a large repo, that'll take some time because it's actually pulling down the whole project history. But that's optional as well. There are options in Git where you can say, don't bother pulling down the whole history, only pull down the latest n commits or something. But sooner or later, you'll find that you'll want access to the entire project history, and then you'll probably want to sort of deepen that clone to make sure you got everything anyway. So yes, there are workarounds, but I haven't actually seen them used that much.
When you say it's expensive, the most common checkout that anybody is going to have is on their build server.
Yeah.
It should be cloning at a depth of what?
Yeah. Oh yeah. So he's basically saying that when your build server is typically checking out your Git repo for every build it does. So there's a new version. Let's check out the new version and build it, and say that all tests are green and all that stuff. And yes, that one should probably not have a full clone, or certainly it shouldn't clone your repo fresh every time it does a build. That's just wasting time and space. Yes, it can clone with a depth of 1, but it can also do a remote call called git fetch pack or something like that. I can't remember. No, git. Yeah, I can't remember the name of the command right now, but there's a command where you can basically say, talk to a server and just give me a tarball of this one version. I don't want to do a whole clone. I just want this one version, and the server will give you that, and you can just build from there. So yeah, there are lots of tools and lots of customization to be done. Yes.
Yeah, and in addition to what you just said, you have the reference repo opportunity as well, where if somewhere else on your local disk there exists another clone, which is a relative of what you're cloning now, you can still say I'm cloning that remote thing. But if you happen to find some of these refs in that other local, bring those in there, because that's a fast operation. We handled by hard links, I think.
Yeah. So say you have 2 Git repos of the same project next to each other on your local disk. You can tell one of those repos to find objects in the other repo, and basically not have to store 2 duplicate copies of the objects directory. And that helps a lot. Say, on the build server, I would typically have some master repo that you don't build from. It's just there to make sure all objects are available locally. And then for each build you do, you basically create a new repo saying that, clone the latest from the server, but use this other repo as a source of objects as well. And you'll find that the clone is much quicker because you already have all the objects available locally. So for those specialized scenarios where you do build or check out a lot, like on build servers, there are solutions to make it go fast, and probably much faster than what you would get from a centralized version control system. Yes?
Yeah, as far as I understood it, after Microsoft has converted their Windows source code to the Git, they actually started working on because that's quite a huge repository.
Obviously.
They started working on a kind of virtual file system thing that allows you to kind of clone but not transfer everything, so that you actually kind of incrementally pull data, even though it looks like your own file system has everything.
Yeah, I've seen similar things where I think there's a Fuse file system for Linux where you mount up the file system and the file system reflects some version of some Git repo, and then basically only when you start accessing the files does it actually get those objects and check them out and basically make them available. So yeah, you basically have Git running underneath your file system layer. Yeah, so yeah, there are tons of tools and things to speed up and help do the things you need to get done. Yeah, that's just one of them. What more questions do you have? Nothing at all? Well, we're at 18:30. That's pretty much it. Yeah, thanks.